Okay, so we're going to be simply proving an integral formula today. It's quite useful. You might see it a few places. It's that the integral of 1 over x squared plus 1 with respect to x is equal to the arctangent of x plus c. Let's prove it by differentiating arctan of x plus c and seeing what we get. So first of all, let's let different color. Let y equal the arctangent of x. This means that the tangent of y is equal to x. Let's do implicit differentiation on both sides. We get that the secant squared of y multiplied by dy by dx is equal to 1, because derivative of x with respect to 1 with respect to x is just 1. Let's divide by the secant squared y on both sides. We get that dy by dx is equal to 1 divided by the secant squared of y, and we could substitute y at this point, and it would be correct, although it wouldn't be in its simplest form. It wouldn't be in this form, and this is what we're trying to prove, so we need to take further, we need to do more work. So, remember the trigonometric identity, sine squared of theta plus cosine squared of theta is equal to 1. If we divide each term by cosine theta, we get that sine squared, divide each term by cosine squared theta, sorry. We get sine squared theta over cosine squared theta, which is just tan squared theta, plus cosine squared theta over cosine squared theta, which is 1, is equal to secant squared theta. So we have this identity relating secant squared theta and tangent squared theta plus 1. And we see this here. Let's substitute in secant squared of y for 1 plus tangent squared of y. So we get that dy by dx is equal to 1 over tangent squared. Let's just write this as tangent y squared plus 1. And now let's substitute y. We get 1 over tangent of arctangent of x squared plus 1. The tangent and the arctangent just cancel, and you're left with dy by dx is equal to 1 over x squared plus 1. And obviously integrating this will yield the original arctan x plus the constant term. I hope this helped for anybody who didn't already know how to prove this. It's not that hard to prove, but it is useful. I hope you enjoyed.